So section 2.2 is going to be on differentiability. So section 2.1 was just on what is this idea of a derivative? And remember, derivative means slope. So we're going to talk about when a derivative fails to exist. So there's a couple different ways. I'm going to give you some very concrete examples in a moment. But basically, you just need to know that your derivative is not going to exist when your derivative from the left does not equal the derivative from the right. So very similar to our limit definition of when a derivative or a limit existed. So a limit exists when the limit from the left equals the limit from the right. Same thing with a derivative. A derivative exists when the slope or the derivative from the left equals the slope or the derivative from the right. So you're going to kind of check both sides. So here's some examples where you might be able to see that they're not the same. So for instance, if y equals the absolute value of x, and you look over here at the graph, you can see that there's a corner there. And this is one time when the derivative does not exist. And the reason for that is, again, derivative means slope. So if you look here, the slope of that line is equal to -1. And over here, the slope of that line is equal to +1. So the question is, what's the slope at that point right there? Because it comes to a point, you won't be able to find a place where the derivative from the left equals the derivative from the right. The derivative from the left will always be -1 at that point, and the derivative from the right will always be +1 at that point. This brings me to another term that we use a lot of times with derivatives, and the term is called locally linear, and that means that if you zoom in many times, or even a couple times, the graph should flatten if it's differentiable. You can zoom in many, a million times on that point right there, and it will never become locally linear. It will always stay a point. And you can try that later on your own if you would like. Another place where a derivative fails to exist is something called a cusp. These always remind me of the seagull graphs that you guys probably used to, or seagull drawings that you used to make in art class in elementary school. The equation is y equals x to the 2/3, and it literally looks like that seagull. Again, differentiable everywhere except for that point right there, because you can see that your derivative from the left does not equal the derivative from the right. And again, if you're not sure, zoom in on that point and you will see that it will stay a point. It will not flatten out, so it is not locally linear. Cusp. So far we have a corner, we have a cusp. Vertical tangent equation, y equals x to the 1/5. It's just an example. Now, it was kind of hard to draw this, but you can see right here, this should be straight up and down. So basically your graph goes in this direction and then it goes in that direction. Well, this section right here where that graph is going to be straight up and down, well, what do you know about lines that are straight up and down, right? The slope would be undefined. So your slope is undefined. Well, what do you know about derivatives? Derivative equals slope. So if your slope is undefined, then your derivative is going to be undefined. So anywhere where you might have a vertical tangent, a line that's straight up and down, a straight up and down slope, your function is not differentiable. Again, it's differentiable every place else. It's just not differentiable where you have that vertical tangent. And the last one is very obvious, where you have a discontinuity. So if you have a discontinuity, you cannot be differentiable the whole function. Again, you would be differentiable here and you'd be differentiable here, but not at 0 because you have a discontinuity. So what would be the slope from the left and from the right? Even though the slope here looks like a 0, you need to have continuity. So if they ever tell you, this is a really, really important one. So if they ever tell you that the derivative exists, then you know that the function is continuous. Okay, so if they tell you that the derivative exists, then you can assume continuity. It does not work in the opposite direction. So if they tell you that it's continuous, that does not imply that it is differentiable. And for all the reasons that I just gave you from above, right? That's a continuous function, but it's not differentiable. That's continuous, not differentiable. That's continuous, not differentiable. But if they tell you that the derivative exists, you must have continuity, and that could be useful later on. Okay, so takeaways from this lesson. In order for a limit to exist, your slope from the left has to equal your slope from the right. And there's 4 main examples of when this does not happen. That's at corners, cusps, vertical tangents, and discontinuities.